Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Normally, when you heat a solid past its melting point, it melts, hence the name. The atoms in the material, arranged in a crystal lattice in its solid state, loses its structure to become a liquid. But there are ways to heat a solid past its melting point without it melting. This is known as superheating a material. Recently, Thomas White, a physicist based at the University of Nevada, Reno, and his team have used a laser to heat a thin piece of gold foil to about 19,000 Kelvin while maintaining the material's crystal structure. That's over 14 times hotter than its melting temperature and much hotter than previously predicted.
We have a 400 nanometer blue laser that comes in and hits the surface of our gold foil. We just dump this energy into our thin gold samples and it heats it up to these extreme temperatures.
They hit the gold with extremely short laser pulses that heat the foil uniformly. The pulses are 45 femtoseconds long. That's 45 quadrillionths of a second long. Their technique heats the gold extremely uniformly and quickly.
The blue laser actually excites what we call ballistic electrons in the surface. So it sort of kicks up a couple of electrons from the front surface, and they stream through the target, carrying the heat through in order to create this uniform heating.
They heat the gold more quickly than the material can expand. For this reason, the gold stays solid, but the phase is very short-lived.
We don't hold off the melting process forever. So after a couple of picoseconds, the whole thing melts. And we see in our experiment that when it melts, it explodes violently and the whole thing sort of disassembles and the experiment is over. So we can only retain these extreme conditions, this extreme superheating state, for a few picoseconds.
White says their group is the first to superheat gold to this confirmed temperature. They had to develop a brand new thermometry technique to do this.
What we've done for the first time is measure the temperature after you fire one of these lasers at a piece of gold.
After using the blue laser to heat up the gold, White's team uses an X-ray laser to take the temperature. They used SLAC's LINAC coherent light source in California, which is the world's brightest X-ray laser.
We take these X-rays and we scatter them off the ions in the material. And if the ion is moving towards us, we get an upshift in energy. And if the ion is moving away from us, we get a downshifted energy, and we can measure this energy shift, and therefore we can directly measure the velocity of the atom in the sample. And as you know, the velocity of the atoms or the velocity distribution is related to the temperature. So we can measure the temperature by just measuring the velocity of all the atoms in the material.
They developed this new thermometry technique to study extreme states of matter in the lab. White takes materials and heats them to extreme temperatures or squeezes them under intense pressures and studies what happens.
Even though you think the temperature of something is such a basic quantity in our everyday life, in these extreme states of matter, we haven't had a good way to measure the temperature accurately for decades. And so that is the problem that we were trying to solve.
By studying these forms of matter up close in the lab, White seeks to better understand what goes on inside planets, stars, and even extreme human-engineered environments such as nuclear fusion reactors.
Our next step is to apply this new thermometer that we have to investigate the conditions that we would find inside planets.
But in the meantime, their demonstration with gold poses some questions about superheating. A previous paper in the 1980s predicted that you could only superheat gold to 3 times its melt temperature, due to a point called the entropy catastrophe. At this point, the solid state becomes more disordered than the liquid state. So beyond that point, the material would have to decrease in entropy in order to melt. In their case, they reached 14 times the melt temperature beyond the predicted 3. However, White says that their work doesn't actually contradict the 1980s prediction because their demonstration involved different experimental conditions. The work in the 80s assumed that the material could expand, whereas White's sample doesn't.
We heat something up so quickly that it doesn't have time to expand. If we reevaluate our experiments within the context of this theory and we prevent expansion, we see that there might be no limit to superheating, or at least a much higher limit at least within this theory, we can't say anymore.
White hopes that these experimental results could open new theoretical investigations into superheating.
The result of our work is to reopen the question, what is the ultimate limit of superheating and how hot can you make something before it melts?
This work was published in a recent issue of Nature. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X @MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.